What is S3? Can someone name it?
It's a symmetric group
On the set of 3 elements. So this is the set of all permutations pi such that pi goes from 3 to 3. And another way to say that is it's the set of all permutations on 1, 2, 3. Or of, I guess you could call it, of 1, 2, 3. Does anybody recognize which notation you prefer? Which notation is easier to visualize?
the
Permutation diagram. We're going to do the actual function notation for giggles. Here is a question for you. Before we begin, let me ask you this. So let's go ahead and say that here's the domain. And we'll go ahead and call this 1, we'll call this 2, and we'll call this 3. And then what I want to do is I'm going to call these elements the codomain. How many different choices do I have for the first element here? 3. I could choose one of 3. The moment I've chosen 1, though, what happens for the number of choices I have in my second element? I have 2 choices. The moment I've chosen the second one, how many choices do I have left for the third one? 1. How many total elements are going to be in S3? Well, I had 3 choices for the first one, 2 choices for the second one, 1 choice for the third one. How many total elements? That implies that S3 has cardinality 3 factorial. Right? The number of things that are available, the number of functions available in that set is 3 factorial. What's another way to say 3 factorial in English? 6. So how many permutations are in S3? 6. Okay, so let's map them all out. Let's map them out. So let's do the first permutation. Could you guess what the first permutation is going to be? Yep. And then why don't we do here, we'll do what we call function notation. And then over here, we'll do what we call permutation diagram. Okay. And then we'll literally just count them. So here, we'll do our first permutation. Okay. How many inputs do I have? 1, 2, 3. Could you guess what we say about the first permutation? Sends 1 to 1, 2 to 2, 3 to 3. So let's go ahead and draw the diagram associated with this. 1, 2, 3. In the codomain, 1, 2, 3. What permutation is it? 1 goes to 1, 2 goes to 2, 3 goes to 3. That's now what we'll call that pi 1. What's that called in the sets that we've been working with? Identity permutation. This is where I would actually recommend not doing this in function first, but doing it in diagram first. Because diagrams are a lot easier to figure out than looking at a bunch of numbers and notation. What's the next choice of permutation that I could use? Map 1 to 2 and 2 to 1 and leave 3 alone. What's it called when I only swap 2 elements? Transposition. So this is what you might call the 1 transposition. What would that look like in function notation? 1 goes to 2, 2 goes to 1. What happens to 3? Not a damn thing. So we'll call that permutation 2. And this is now a transposition. And you could actually write of 1 and 2. Okay. Let's take a look at the next one. What's the next one there? Okay, so that's kind of a natural choice. 1 goes to 3. 3 goes to 1. 2 goes to 2. What do you notice about this thing? Let's go ahead and check. Let's call this number 3. 1 goes to 3. 3 goes to 1. What happens to 2? Not a damn thing. This is also known as a transposition of 1 and 3. How many do I have left? I've done 1, 2, 3. There's a total of 6. I have 3 more. What's the last transposition possible here? Yeah. Omar, I'm going to offer you a proof that I have finished. I've done this proof actually in 3 different ways in my life. I'm about to give you a conjecture in about 3 minutes. It's a nice one. You don't need abstract algebra to prove this conjecture either. Yeah. So here we go. This is going to be the transposition of what? To the whole class, actually. The challenge I'm about to pose is to the whole class. OK, so what's that particular permutation look like? What does it do? What does it do to the number 1? Nothing. What does it do to the number 2? 3. What does it do to the number 3? 2. OK. What's undone here? Which permutations have we not finished yet? OK. Those are called cycles. And in this one, we'll call it a 3 cycle. Could you imagine why we call it a 3 cycle? Because there's 3 of them, right? Yeah, so 1, 2, 3. 1, 2, 3. OK, go ahead.
1 goes to 2, 3, 3 goes to 1.
OK, so now we go permutation 5. 1 goes to 2. Permutation 5, 2 goes to 3. Permutation 5, 3 goes to 1. That's our first cycle. 3 cycle because there's all 3 of them. How would I know that it's onto? What does onto mean? It means everything in the codomain is hit. What's another way to say that in the diagram? Every element in the output has a line connecting. What does it mean? A line connecting means it's mapped to an input. What does it mean 1 to 1? Every input has only one line out. Let's draw a map between 3 and 3 that is not 1 to 1. Yeah?
But you said that 1 to 1 means that every input has only one line out?
One line out.
I disagree with that. If you have 3 and 2 go to the same place.
Oh, I'm sorry. Every output has only one line in. Yeah, sorry about that. Yeah. Thank you for that. 1 to 1 means that this can never happen, right?
Oh, yeah. That's true.
Yeah. Function means this can never happen.
Oh, correct. Okay.
Function means you'll never have an input with 2 outputs. 1 to 1 means you'll never have one output with more than one input.
Well, if it's a 1-to-1 function, then you can't have either.
Yeah, but you could 1-to-1 functions are not always onto, right? This 1-to-1 function is not onto.
Yeah.
In permutations, the fact that your domain space is equal to your codomain immediately implies that 1-to-1 is equivalent to onto, and onto is equivalent to 1-to-1. Those are equivalent conditions, knowing that the cardinality of your 2 sets are equal. Right?
Yeah.
It must be, right?
Yeah.
So what's the other cycle that we haven't hit yet? Yeah, so 2 would go to 1, 3 would go to 2, and 1 would go to 3. So here we would have the 6th permutation. 1 went to 3, 2 went to 1, and what? 3 went to 2.